Welcome back to Calc 2. Today we're looking at Chapter 11, Lesson 4, Graphing Polar Coordinate Equations. The first topic the book introduces symmetry in polar equations. Just as in Cartesian coordinate plane, we have symmetry about the y-axis over the x-axis, about the line y equals x and line y equals negative x. We also can test for symmetry in polar equations. There are three tests for symmetry in the polar plane. The first is symmetry about the x-axis. If a point r theta lies on the graph, then we can substitute in the point r negative theta into the equation. If we get back the same equation as r theta, then we'll have symmetry about the x-axis. We can also test for symmetry about the y-axis. So again, if we have a polar equation in the form r theta, we can use the test point negative r negative theta. If we get back the same equation, then we're going to have symmetry in the y-axis. Our final test is symmetry about the origin. To get symmetry about the origin, we're going to use the test point negative r theta. If we plug negative r theta into our equation, and we get back the original equation, then we have symmetry about the origin. Here are three graphs that illustrate that property. Again, if we have a function where we have a point r theta, and we evaluate that same equation for r negative theta, that means we're going to have symmetry, a flip-flop, a reflection over the x-axis. If we plug in the point r theta and replace that with negative r negative theta and we get back the same equation, again that means we have symmetry over the y-axis. And again, if we use our test point negative r theta, then we're going to have symmetry, rotational symmetry about the origin. We're going to look at a couple examples. I will say, and just acknowledge the obvious, all of these graphs can be graphed, just checked by either using your TI calculator and switching it into polar mode, or again, just going to Google and typing in the equation. You can find lots of graphing utilities to check all of these graphs just using the good old Google machine. We do have a slope for the curve, f of theta in the Cartesian plane. None of the examples use this problem, but you can find the graph then for the slope of a curve in polar form by taking the derivative of the equation r theta by the first derivative of theta times sine of theta plus the function of theta times cosine of theta all over the first derivative of theta times cosine theta minus the function of theta times sine of theta. The book proves that or derives that formula as well. There's a couple example problems in the homework that will use that formula. For example 1, then let's graph the curve r is equal to 1 minus cosine theta in the coordinate plane. First thing we want to do is test for symmetry. Again, we have three types. The first is, let's test for reflection about the x-axis. To test for symmetry over the x-axis, we're going to use the test point r negative theta. There's one identity, or actually a couple identities we need to remember, and that is that cosine of negative theta is the same as cosine of theta, versus sine of negative theta does keep the negative, and that is negative sine of theta. So we're going to use our test point r negative theta, and we're going to plug that into our equation. That's going to give us then r is equal to 1 minus cosine of negative theta. But as our trig identity tells us, that then that just reverts back into 1 minus cosine of theta. Because we get back the same equation, therefore we have to have symmetry in the x-axis. The other two tests would be for y-axis symmetry. That's going to be negative r negative theta. But if we plug that in, we're going to get negative r equals to 1 minus cosine theta. That's not the same, so we do not have y-axis symmetry. We can do the same thing for symmetry about the origin, which is going to use the test point negative r theta. And again, we're going to get the wrong equation. We're going to get negative r is equal to 1 minus cosine theta, which is not the original equation, so we do not have symmetry about the origin. Now to graph our equation, we can look at a table. So if we look at theta and then r is equal to 1 minus cosine theta, we'll look at some easy values. So let's look at 0. We'll pick the easy one. So pi thirds, pi halves, 2 pi thirds, and pi. And if we plug that into r, it's equal to 1 minus cosine theta. That's going to get a 0, 1/2, 1, 3.5, and 2. If you're not getting good values or your values don't go far enough, you might want to consider smaller values of theta or even possibly larger values of theta. But we're going to, again, use the fact that we know that our graph has x-axis symmetry to help us graph our polar equation. So we're starting at 0, 0. And then we're going to be at a theta of pi thirds, so we're off at 60 degrees, and we have a value that's about 1/2. Then we're at 90 degrees with a value of 1. We're at 2 pi thirds, which is going to be 60 degrees up in the second quadrant, or 120 degrees. And so we're going to get a point, and that is the less than 1, so that's 3.5, so we're shrinking back in. And then we're going to get a value, that's bigger than 1, so maybe more out here. And then we're going to get a value at pi, 180 of 2. So we're starting off over here, we're curving up, back and around, and then now we can use the fact that we have x-axis symmetry to flip the graph and model it the same in the other direction. So I'll put some points down here. And so here's our symmetry coming back. This graph does have a special name. This is a cardioid. Card meaning heart, or heart-shaped graph. Again, you can check this by putting it into a graphing utility on the interwebs. Example 2, graph the curve r squared is equal to 4 cosine theta in the Cartesian xy plane. Again, let's look for our symmetries. Again, we have x-axis. For x-axis, we're going to plug in r negative theta. If we plug in r negative theta, again, cosine of negative theta turns back into cosine of theta, so we get r squared equals 4 cosine of theta is the same. So we have to have an x-axis symmetry. For y-axis, we're going to make both negative, so we're going to plug in negative r negative theta. And that's going to give us, now here we're going to square the r, so negative r squared is going to give us back r squared is equal to 4 cosine theta. So here we're going to get symmetry also in the y-axis. And then finally, let's check for symmetry about the origin. That's going to be negative r theta. But again, we're going to square the negative. So negative r squared turns back into r squared equals 4 cosine theta. So it turns out this graph has all 3 symmetries: x-axis, y-axis, and origin symmetries. From there, again, we're going to look at a graph by looking at a table of values. And so we can look at here, let's look at some thetas. And then because we're evaluating a couple things, we might want to check cosine of theta first, is what the book does, but we can just go ahead then and plug that into r is equal to 2 square root cosine of theta. When we solve for r, we're going to need to square root. And so the square root of 4 is 2, and then we're left with cosine, the square root of cosine of theta. So let's check some values. So for theta, let's check maybe 0, pi sixths, pi fourths, pi thirds, and pi halves. So we're checking the main values in the first quadrant. When we plug those in, we're going to get at 0, we're going to get 2. At 30 degrees, we're going to get 1.9. At 45 degrees, we're going to get 1.7. At 60, we're going to get 1.4. And then at pi halves, we're going to get 0. And so let's see what that graph looks like. So at an angle of theta, we're going out 2 units. At an angle of 30 degrees, we're going to be at 1.9, so that starts to come in a little bit. At 45 degrees, we're going to be at 1.7. At 60 degrees, we're going to be at 1.4. And then at 90 degrees, we're at 0, or the origin or the pole. But we're not in polar, we're in Cartesian coordinates, so we're back at the origin. So we get a graph that's a half circle, and now again we can use our symmetries, and it doesn't matter which symmetry you use first. But for example, we could look at x-axis symmetry, so we're flipping over the x-axis. That gets us a circle on the right hand side, but we also have symmetry over the y-axis, which means we also have a graph over on the negative side as well. That also matches in with our origin symmetry. So if we flip our graph 180 degrees about the origin, we're going to get the same graph as well. And there's a graph. Again, you can check this using graphing utilities, either on your graphing calculator or, again, typing that into Google. You'll find all sorts of graphing utilities you can use. Example 3, graph the lemniscate. Again, let's check for symmetries. For x-axis symmetry, we're going to check our r negative theta. Again, now we're going to get sine. So remember from trig, sine of negative theta is equal to negative sine of theta. So if we plug in a theta here, we're going to get r squared is equal to sine of 2 theta, but the sine spits out the negative to stay in front, so that's not the same. So we do not have x-axis symmetry. Next, let's check y-axis symmetry. For that, we're going to check negative r negative theta. If we square negative r, we're going to get back r squared, so that part works. But again, our negative theta is going to be negative sine of 2 theta, so that part doesn't give us back the same equation, so we do not have y-axis symmetry. Finally, we can check origin symmetry, or symmetry about the origin, which is negative r theta. That one will work because when we square negative r, we're going to get back r squared equals sine of 2 theta. So this graph has symmetry just about the origin. Again, to graph this on a graphing utility or in your calculator, we need to solve, so we're going to square root both sides. So we're going to graph r is equal to the square root sine of 2 theta. When you check that one on your graph, you're going to get a graph that looks kind of like a figure 8, but it's in the first and fourth quadrant. And this graph has a special name. This is a lemniscate. And again, we can see here, there's our symmetry about the origin. This is Calc 2, graphing equations in the polar plane.